So we are looking at the effect of the alloying elements, particularly silicon and aluminum, on the evolution of microstructures. So if you look at the sequence of microstructural formation in steels, the first reaction you would expect to see even much before the solidification is started, see inclusion formation. So if you look at the first reaction that happens in a microstructural evolution is the inclusion formation, and inclusion forms much higher temperature than the solidification in liquid regions, especially if you have an oxidizing elements such as silicon and aluminum. You readily oxidize these elements in a liquid stage, and you form the oxides of aluminum and silicon. And subsequently, when you cool down upon reaching the solidification start temperatures, so you will nucleate delta ferrite in steels, even in advanced sites in steels, in conventional advanced sites in steels like in DP and TRIP, and you will solidify first into delta ferrite, and subsequently the alloying elements either can go to liquid or can even partition towards delta ferrite, and especially in aluminum, and other elements will try to partition towards liquid, and subsequently when solidification completes, it becomes it undergoes during solidification based on the carbon concentration, a peritectic reaction, and then a fully austenitic microstructure develops. And subsequently, based on the cooling rates, austenite can either transform to low temperature products or even martensitic based on the cooling rates. So in this reaction, if you look at it, the first rate controlling reaction for subsequent microstructure evolution is the inclusion formation. So inclusion can be engineered, formation can be engineered to our favor. For example, if you have the size controlled the inclusion that are formed, and the inclusions are all also act as potential nucleation sites for the subsequent phase transformation from austenite to room temperature. For example, the acicular ferrite is known to nucleate on the inclusions, non-metallic inclusions present in the microstructure. So if you carefully control the inclusion density, size and volume fraction, and you may also promote the nucleation of acicular ferrite when the austenite is cooling to room temperature, the nucleation of acicular ferrite is seen as an advantageous, because acicular ferrite gives the best toughened microstructure in terms of properties. Having an acicular ferritic microstructure is beneficial instead of having a fully martensitic microstructure. So by carefully manipulating the size and volume fraction, and we can also change the microstructure formation when the austenite it transforms to any other low temperature products during cooling. So the understanding nucleation formation mechanism is very important to control the microstructure at subsequent cooling to room temperature. And if you look at an inclusion formation mechanism, as I said, the first reaction that happens when well pool solidifies, inclusion formation. So inclusion can form at very high temperatures. So when you expose the liquid pool to atmosphere, or even shielding gas if it contains the contamination from oxygen, and the elements like aluminum, silicon can readily combine and then form oxides. And these oxides can trap the alloying elements in the liquid onto the surface. For example, if you look at a typical inclusion in advanced sites in steel, what you see over here is the globular oxide inclusion. So in this case, this steel, so in this case, it's a silicon based inclusion, silicon based strip steel, so SiO2, silicon oxide, for example. So once you have an oxide formed, the other alloying elements like manganese and the sulfur, they are all getting trapped at the surface of the inclusions, wherein you have an epitaxial enrichment of these alloying elements. Like for example, manganese, silicon would go and enrich these surfaces, and you will end up forming the layers of non-metallic inclusions where the oxides at the center, and then because of the epitaxial enrichment of other elements, you will end up forming silicon oxide, manganese sulfide, and so on and so forth in subsequent cooling. And you see in various morphologies based on the temperature also forming. So you have an invariably at the middle you have oxides of silicon aluminum, and then an epitaxial enrichment of the other inclusions that are formed in and around the oxide inclusions. And if you look at the elemental mapping, it can be very clear. So if you look at the distribution of alloying elements in the middle, so this is the oxide. So in this case, in a silicon based strip steel, at the middle you have an enrichment of silicon, and so you will have an silicon peak, and subsequently once you have a silicon oxide formed, and it traps the elements like manganese and sulfur, and then you will have an manganese sulfide forming surrounding the oxide that forms at higher temperature. And so you will have a typical non-metallic inclusion containing silicon oxide at the center, and then manganese sulfide surrounding the silicon oxide. So same you may find it in aluminum based strip steel as well. Again, aluminum oxide forms even higher temperature than silicon oxide, and you will have an aluminum oxide formed, and subsequently you will have an enrichment of silicon and aluminum oxide. Then you will have an silicon oxide surrounding the aluminum oxide, and subsequently you will have a manganese and sulfur enriching these oxides and forming complex non-metallic inclusions. So the mechanism of inclusion formation in advanced iron steels wells, it is it is as in a conventional inclusion formation. You will have an first aluminum oxide formed. So invariably in a trips steel containing aluminum, so you first form the core of aluminum oxide, and once you have aluminum oxide nucleation, and then you will have an enrichment of silicon oxide, enrichment of silicon leading to silicon oxide formation surrounding the aluminum oxide, and subsequently manganese sulfur can also enrich and forming manganese sulfide. So the inclusions morphology appears complex with the presence of an oxide core and then subsequent enrichment of manganese sulfur leading to a complex non-metallic inclusion formation in an advanced iron steel well pools, especially if you have the highly oxidizing alloying elements like aluminum and silicon. And inclusion stability is also affected by the presence of varying amount of oxygen in the atmosphere. So if you have shielding gas when you use or backing gas in a GMAW, or if you use an sort of cover the backing gas in laser beam welding, so presence of oxygen should be controlled significantly, and if you change the oxygen concentration in the weld regions, so your the inclusion formation the kinetics of inclusion formation can also be changed significantly. For example, in this graph I show the weight fractions of inclusions that are commonly observed. The weight percentage of inclusion that commonly observed in trip steels as a function of temperatures with two different oxygen concentration. In the well pool, when you are exposing the well pool of aluminum containing trip steel with two different oxygen concentration, and you will have this is 20 ppm and 40 ppm of oxygen. So in higher oxygen concentration, if you have 40 ppm of oxygen, the inclusion formation temperature is about 2100 centigrade, and subsequently so when you cool down, so obviously you tend to form more volume fraction of aluminum oxide inclusions, and you end up having an 0.008% of inclusions. So if you decrease the oxygen concentration, obviously the amount of non-metallic inclusions you form, it also decreases. And subsequently, when you cool down because of entrapment of manganese and sulfur in the inclusions, oxide inclusions, you will also have manganese sulfide formed. And the formation of manganese sulfide is not influenced by oxygen. So the oxygen would severely affect the volume fraction of oxide inclusions that are present in the well pool. Similarly, the same behavior can also be observed in silicon based trip steel. So if you increase the oxygen concentration present in the pool to react with the silicon in the liquid metal, and you may also change the inclusion volume fraction as well as the kinetics of inclusion formation. So if you have a higher amount of oxygen, you may also have a more volume fraction of silicon oxide, and if you decrease the oxygen concentration, the inclusion concentration in the microstructure also decrease significantly. So the other effect what we generally see in an aluminum based trip steel is the partitioning of aluminum to delta ferrite, and this can be seen in almost all the welding processes when you either use a laser resistance spot welding or laser beam welding or gas metal arc welding. And you see a stabilization of delta ferrite, especially if you have an aluminum concentration ranging from say 1 to 1.2 weight%, and you will have a distinctive layer of delta ferrite stabilized at the fusion boundary as well as along the grind boundaries when you have partitioning of aluminum to delta ferrite. So how it happens? So this stabilization, if you look at an elemental mapping, elemental analysis along the fusion boundary, if you look at it in a trip steel containing aluminum, the weld on the fusion boundary, you would see when you have a delta ferrite stabilized at the fusion boundary, you will have increased amount of aluminum at those regions. So what does aluminum do when aluminum is present in the pool when solidification happens? So aluminum is the in this system is only alloying element which actually partitions to the delta ferrite during solidification. So if you look at this the graph, what I show here, the amount of elements present in the liquid, and so elements and phases present in the liquid as a function of temperature. So if you look at carbon, even starting from the temperature of 2200 degrees centigrade, so carbon is in the liquid present, and the moment you have a solidification, then what happens? Carbon tend to go to liquid and segregate liquid. That means that when you have a delta ferrite solidifying liquid, and delta ferrite sends the carbon or the partitions the carbon to the liquid, and because of that you have an enrichment in carbon in liquid, right? And similarly the manganese also have a similar partitioning behavior, and silicon as well, and partition to liquid. Whereas in aluminum it has an opposite partitioning behavior compared to carbon, silicon, manganese. So aluminum partitioned towards the delta ferrite. That means that liquid is depleted in aluminum. Okay, so the aluminum segregates to the delta ferrite, and because of that, once you have aluminum concentration in delta ferrite increases significantly, and delta ferrite stabilizes to room temperature. So for example, if you look at the maximum aluminum concentration in ferrite, so it can go as high as say for a given 1.1 bulk aluminum concentration, okay, 8%. So when solidification happens, and it can go as high as 1.2, 1.3 in delta ferrite. So once you have aluminum concentration goes beyond 1.2, if you look at a conventional iron aluminum phase diagram. So when aluminum concentration goes above 1.2, and you stabilize ferrite. So, because of the partitioning of aluminum to the delta ferrite, when the solidification happens in aluminum based strip steel, when the delta ferrite concentration goes above a critical limit, say in the pure aluminum iron aluminum system, if it goes on more than 1.2 weight% roughly, and then the system, the microstructure is stabilized to a single phase delta ferrite. So, that is what you clearly see in the aluminum containing strip steel fusion boundary. So, when the liquid solidifies into delta ferrite, so aluminum partition towards delta ferrite, and when the delta ferrite concentration in aluminum reaches beyond 1.2 weight%, and the delta ferrite cannot transform to austenite. So, this delta ferrite remains as an delta ferrite at room temperature even after cooling to room temperature. So, because of that, we have a very soft microstructure in between a mattacidic microstructure in the heat effect zone as well as in the rest of the fusion boundary, and leading to strain partitioning when you are applying to load. We will see in detail how these delta ferrite can change the microstructure the distribution, especially the distribution of retained austenite and the mechanical properties of the weldments because of these the presence of soft delta ferrite in aluminum based strip steel. And this effect is not seen in silicon based strip steel because silicon is not that effective in stabilizing ferrite or even in stabilizing in the other microstructural phases, and because of very strong affinity for aluminum to delta ferrite, and then beyond say 1.2%, 8% to 8% aluminum, if present in delta ferrite, and delta ferrite gets stabilized, and then it cannot transform to austenite in subsequent cooling. So, if you look at it now, the complexities in microstructure development because of these alloying elements. So, we need to now understand the basics. Without understanding these basics, and we cannot modify the Weld thermal cycle. So, I just showed you two examples of the effect of the alloying elements such as silicon aluminum, which are very important to stabilize retained austenite. And if you have these two alloying elements, you already see a tremendous change in the distribution of microstructure in the fusion boundary, in the fusion zone microstructure. So, we will go in detail how the other alloying elements behave during welding and how the microstructure evolves in the heat affected zone during cooling from higher temperatures. We will also see how we can favorably modify the Weld thermal cycles or add other alloying elements to our favor, so that we can minimize the damage these alloying elements do to the weld microstructure.